Alright, welcome back to our last lesson for the electrochemistry unit, and this is a course on electrochemistry with regards to science, technology, and society. So this whole section kind of revolves around how electrochemical cells, specifically a lot of electrolytic and of course even some voltaic, was used to kind of just solve practical problems that were found throughout society. So there is a little bit of reading if you do want to hop on and use digital books. You can read page 634 to 635 to help complete the information, or you can watch this and we'll kind of go over it. So first thing, corrosion. Now, corrosion for metals is basically an oxidation because we're starting with a metal like iron, solid, and then of course it's losing electrons turning into the iron ion or a metal ion. And of course that is a problem because if we're building stuff from metal, we don't want it to corrode or oxidize. So, corrosion, or oxidation, is an electrochemical process in which a metal, solid, reacts with substance in the atmosphere. Now, the substance in the atmosphere that we are going to be dealing with is water and oxygen. And this is going to return the metal to its ore-like state. So basically how it existed in nature before we took it out of the ground, find a way to refine it to produce that metal. Because of course everywhere in the world there's water and oxygen, so of course this is just how basically the metals existed before we took them and extracted them. So of course this is a problem because oxidation of metals causes a loss of structural integrity. So of course if we build stuff from it, it's not going to last, it could break, and that can cause all kinds of problems. So the oxidizing environment, the half reaction that occurs is of course oxygen in the air, which is O2 gas, plus our water, 2H2O liquid, plus, plus 4 electrons, produces 4 hydroxide ions. And of course this half reaction can be found in our data booklets, which if you do find it, it is a fairly strong oxidizing agent, which is right here. So notice it does have a reduction potential of a positive 0.40 volts, which is still rather strong. So that means that if this right here, sorry, didn't mean to make that too big. So if these right here, if this is our strongest oxidizing agent, that means any metals that are below this, so for example, lead, tin, nickel, cobalt, cadmium, iron, zinc, chromium, aluminum, magnesium, sodium, calcium, barium, potassium, and lithium. So all of these here can have a spontaneous reaction inside the environment, which can be bad. And of course iron being extremely common, being below here, so this is one of the main reasons why when we started doing a lot of working with iron as society, we had to find a way to kind of stop this reaction here. So of course any metal as a reducing agent below that half reaction will spontaneously oxidize over time. Now if salt is present, this will actually speed up the oxidation because it acts as a salt bridge. So this is why in a lot of places like coastal regions you do get rusting of cars that happen a lot quicker. Even during winters, if you put salt down on the roads, that causes your cars to rust a lot sooner just because the salt will act as a salt bridge, speeding it up. So that's why cleaning your car is also very important in maintaining it, keeping it, the longevity of it. So of course preventing and dealing with corrosions are economic and of course technological problems. That scientists had to figure out over time to try to stop these things. So this is a diagram of kind of what happens inside of a water bubble of why stuff corrodes. So this is our water droplet right here. Now inside of that water, of course, we get our oxygen that'll just come in here, and then we get our oxygen plus our water that will then oxidize this solid piece of iron right here into our iron 2. And of course that is just the corrosion. So of course we do need that combination of both water and oxygen in order to cause these reactions. So on this page right here, of course, the cathode, anode, and net redox reactions, we can actually write all these down. So the reduction half reaction that's occurring is, of course, our strongest oxidizing agent. In this case was our oxygen gas plus our 2H2O liquid plus our 4 electrons, producing 4OH minus. And our anode, or our oxidation half reaction, was our solid iron, turning into solid 2, or iron 2 plus, aqueous, and of course our 2 electrons. And of course the net redox, if we wanted to add two of these half reactions together, we have to multiply the iron half reaction by 2, so we get the total number of electrons equaling out, and our net reaction is O2 gas plus 2H2O liquid plus 2 Fe solid, producing 4OH minus plus 2Fe2 plus. And then of course when these dry here, they can then produce iron hydroxide. So we are going to look away to actually how to prevent this, or some technological processes that came out to actually stop this from occurring. So once again, this is bad. So some metals can have a natural prevention. Iron isn't one of these here. So most metals develop a thin oxide coating, which then protects from the outer surface from further oxidation. Now, this is useful, but the problem is that in most cases, the oxide coating will scale off because it's very brittle. And this leaves the metal surface exposed, and then it can then corrode even further, or create another oxide coating. That'll fall off, and then another one will form, and so on and so on. So over time, it'll just start getting thinner and thinner and thinner. So scientists need to figure out a way to actually prevent this. So they came out with some technology. So one of them, a protective coating, right? So one of the ones, paint. Works great. So if we paint a surface, it is completely covered, and it must remain intact, so no scratches or chips, right? So basically, as long as you have paint over something and there's no chips or anything like that, you're not going to get oxidation because the surface isn't exposed. Now, obviously, and this is why if you do get paint chips in your vehicles and stuff like that, you need to repair it right away, because if not, it will rust, right? And that is because you get exposed iron. Now, another way, a protective coating, and this is a little better than paint because it doesn't really scratch as easily, and this is metallic coatings, because obviously metals don't scratch very well, or they won't kind of chip off like paint. And this is when we can get coatings like zinc, chromium, or tin that can be plated onto other metals, so we don't need to worry about our iron corroding. So, of course, if then an oxide layer forms on these here, well, it's forming on those and not the iron, so the structural integrity of the iron will remain intact. So how do we get these metallic coatings on other metals? Well, it's something called electroplating. Now, this is a technique where a thin layer of desired metal is used to coat, or quote-unquote plate, an object that's needed. So this process is often used to protect objects against corrosion, or to improve their appearance. So for example, chromium is extremely shiny, so plating chromium or chrome onto other things will just give it a better look. Or electroplating gold on silver items, so jewelry and everything like that, just makes it look better. So of course, plating of metals need to occur at the cathode of electrolytic cell, because that's where reduction occurs. So for example, like this is super common, so instead of having like flatware that are pure silver, you get silver plated things. So this is just when we have an electrolytic solution containing silver ions that's going to plate our metal. Of course, we need a power source and the 2 electrodes. Now, generally the object being plated is at the cathode, just because that's where reduction needs to happen. So if we had to look at a diagram of a spoon being electroplated with silver, we can fully label our diagram, because we know how a general electrolytic cell looks, right? We'll have one thing right here. Now we're going to have this, our anode, and this is going to be silver solid. This is going to be hooked up to a power source, and then we are going to have our cathode. Now in this example right here, if we're trying to electroplate, in this case here, a spoon, so our spoon is actually going to be Well, that's a terrible looking spoon, but still this is going to be our cathode. Of course, it's fully submersed. So this is our spoon, cathode, and this is our spoon. And of course, we'll have a solution of silver ions. Now, the reason why we're still going to have silver ions is that as the cell operates, electrons are going to leave here, so we're going to get oxidation at the anode. So we're going to get this silver electrode here kind of decreasing in mass, supplying more silver ions, and the silver ions are going to go over and deposit at here. That is generally what's going to happen. In reaction at cathode, we get our silver ion is going to react with an electron and produce our silver solid, and that is how we electroplate metals onto other objects. So that's just kind of how electroplating will work, and you'll notice that really it's the exact same diagram we've seen before. The only difference is the cathode right now is just the object that we're trying to protect or plate with something, and that can be anything. Now, other ways to protect certain objects, of course, putting coatings on certain things will definitely help, but another way we can do it is something called cathodic protection. Now, cathodic protection, remember, reduction happens at the cathode. So having cathodic protection, we're forcing the metal to be protected by becoming the cathode, by using an impressed current or a sacrificial anode. So what that means is we're forcing the metal being protected to become the cathode, so it's not going to react in the reaction. It's just going to have a reaction occurring on it. Because remember, a cathode is just a solid, which helps transfer electrons for the reaction to occur. So first, let's look at impressed current. So an electric current is forced to flow towards an object by an external voltage, so this requires a constant power supply. So how this works, for example, if we have, let's say, this is underground, and we have an iron fuel tank. Now, if we just have this iron fuel tank buried, right now we're going to get our oxygen and water will react with the iron, and we're going to get rust forming, which of course is bad. But if we hook up a power source and connect it to our tank, and we force the electrons through here, now for this half reaction of our oxygen plus our water, was it 2H2O plus 4 electrons producing 4OH minus. Now, normally in rust, these electrons right here that it needs are going to come from iron. But now these electrons right here are supplied by the power source and not iron solid. So by having this power source hooking up, it's supplying, of course, a source of electrons. Of course, the electrons are flowing over the iron tank, and then these electrons are readily available, so the oxygen and water are going to pick up the electrons from the power source and not from iron. So that is what the impressed current means, is that it's supplying that constant supply of electrons so that the iron will not oxidize, but it's picking up the electrons from the power source. So that is one way to protect. The other one is something called a sacrificial anode. So of course, if you kind of break down that word, sacrificial meaning something's going to sacrifice, anode meaning that something's going to be oxidized. So this is when a metal that is more easily oxidized than the metal being protected is connected to the object being protected. So for example, a sacrificial anode is used to protect steel, or specifically the iron steel, in a buried fuel tank, pipelines, as well as metal surfaces in boats, ships, and everything like that. So this is a very common thing. Now, a more active metal is slowly consumed, right, or oxidized at the anode, protecting the other metal. So what this means, if we look at our data booklet, end. We see iron right here. Now, normally we would have our strongest oxidizing agent right here, and now this is our strongest reducing agent. But if we manage to connect, let's say, another metal that is a stronger reducing agent, so for example, zinc. Now notice how zinc right now is strongest reducing agent. So if you do our 5-step method and you write out everything that's there, you know, we have oxygen and water combining for our strongest oxidizing agent, but now if you wanted to see what will react first, either iron or zinc, zinc is the stronger reducing agent, so that will actually oxidize, saving iron. And that's what we have right here. In this case right here, sacrificial anode is magnesium. So if you have, let's say, a big chunk of magnesium that is connected to this iron pipeline by an electrical wire, now as the oxygen and water get attracted to that iron, it undergoes its reduction half reaction. Instead of iron supplying the electrons are going to flow from magnesium, go over here, and now the electrons from the magnesium react with that. And then of course the iron is saved because the magnesium undergoes its reaction of Mg solid, producing 2 electrons and Mg2+. And then of course magnesium ions going inside of the soil. Super handy. Plants use magnesium all the time in order to grow and everything like that. And finally, last but not least, how we protect stuff is creating an alloy. So an alloy is just a mixture of metals that changes the reduction potential. So that's why you'll notice inside of our data booklet we don't have any alloys. So for example, like stainless steel is chromium and nickel, and it changes steel's reduction potential to where it's almost like a noble metal like gold. So it's basically unreactive. So this is why stainless steel doesn't rust. Even though we have a combination of chromium, nickel, and iron, which when we look at our data booklet, chromium is here. So I'll just kind of highlight all of them here. We get a combination of chromium, nickel, and iron. So for some reason, when you look at these here, these are all fairly strong reducing agents. They're all below this right here. So technically, individually, these will all react to corrode. But for some reason, when you have a combination of all these here, it actually increases its reduction potential to almost up here to that similar of gold. So once again, to create these alloys, it's mostly a lot of trial and error. Like there's no formula you can plug in and it'll tell you what reduction potential it is. It's just that over the years, through lots of trial and error, people have found out like certain ratios of how to mix things together and get a specific reduction potential. So that is it for the electrochemistry unit. So of course there's the assignment on everything that's there. So try to get that done on time. And of course, if you need to go over anything, we'll have our help session this Thursday, and next unit is our last one. It is on equilibrium with a concentration of acids and bases. So we have lots of time to kind of get through that one. But anyway, we'll start that one next week. So good luck with this unit, and I'll see you guys later.